4.8, Analyzing Graphs of Polynomial Functions. So to start off, we have a core concept or a concept summary, zeros, factors, solutions, and intercepts. So we let fx equal that whole number and let that be a polynomial function. The following statements are equivalent. If it's 0, k is 0 of the polynomial function f. Factor, x minus k, is a factor of the polynomial fx. Solution, k is a solution, or root, of the polynomial equation fx equals 0. X-intercept, if k is a real number, then k is an x-intercept of the graph of the polynomial function f. The graph of f passes through k, 0. So for our first example, we have using x-intercepts to graph a polynomial function. Graph f of x equals x minus 2 squared times x plus 1. Step 1, find and plot x-intercepts. So the x-intercepts are going to be 2 and negative 1, as you can tell from the first part of the equation, where x minus 2 and x plus 1. So the points will be 2, 0, and 0, negative 1. Step 2, plot points between and beyond the x-intercepts. You can also plug this equation into your calculator and your set, and you'll get this table. And I circled the x-intercepts. Step 3, determine the end behavior. To do this, plug the equation in your calculator and look at the table. The x values are negative along with the y values, and the x values are positive along with the y values. So the end behavior is fx goes to negative infinity as x goes to negative infinity, and fx goes to positive infinity as x goes to positive infinity. Step 4, draw the graph and plot it with the correct points. As you can see, they pass through the x-intercepts and all the points that I put on the table earlier. So we have another core concept, which is the location principle. If f is a polynomial function and a and b are two real numbers such that f of a is less than 0 and f of b is greater than 0, then f has at least one real 0 between a and b. Example 2, locating real zeros of a polynomial function. So the equation that we're going to do today is x cubed minus 4x squared minus x plus 4. Step 1, use the graphing calculator to make a table. I put what I put down on my calculator right here for step 2, and I circled the ones that pair up with 0, which is step 3. So whichever x has a y pair that equals 0, that is one of the real zeros. In this case, there are 3 real zeros, and they are negative 1, 1, and 4. Also, you can check this using synthetic division just to make sure you're completely right. So the vocabulary we have is the y-coordinate of a turning point is a local maximum of the function when the point is higher than all nearby points. The y-coordinate of a turning point is a local minimum of the function when the point is lower than all nearby points. And here I put the graph that they had in the textbook, just to make it more clear. So we have yet another core concept, which is turning points of polynomial functions. 1, the graph of every polynomial function of degree n has at most n minus 1 turning points. 2, if a polynomial function has n distinct real zeros, then its graph has exactly n minus 1 turning points.
Example 3, finding turning points. Take the problem x cubed minus 3x squared minus 6. Use your graphing calculator to solve. You can find the local minimum and maximum with your calculator. Plug the problem in and then hit the second key and then the trace key. Go down to minimum first. It will ask you for the left and right. The local minimum for this problem is 2, negative 10. Repeat these steps for the maximum value. The maximum value for this problem is 0, negative 6. Core concept, even and odd functions. A function f is an even function when f of negative x equals f of x for all x in its domain. The graph of an even function is symmetric about the y-axis. A function f is an odd function when f of negative x equals negative f of x for all x in its domain. The graph of an odd function is symmetric about the origin. One way to recognize a graph that is symmetric about the origin is that it looks the same after a 180-degree rotation about the origin. For an even function, if x and y is on the graph, then negative xy is also on the graph. For an odd function, if xy is on the graph, then negative x, negative y is also on the graph. For example 4, we'll be identifying even and odd functions. Take f of x equals x to the fourth minus 7x squared plus 1. For step 1, replace x with negative x and then simplify. And then for step 2, because f of negative x equals f of x, the function is even because there was no change. Thank you.